This video will explain the fundamentals of water flow in soil and will also look at some engineering problems that may happen when the water seepage is too high in soil. As we know that water can flow through soil because soil is very porous material and there is enough space for water to seep through. Let's look at this example where we have a river and we have a river bank. There is some engineering structure, which is levee. And you will see that on the left-hand side in the river we have a water level at this point. And then down the levee, we'll see that there is another level of water. It's probably groundwater level, something around here. And because of the difference in these two levels, water will flow through the soil. It will seep through the soil because of the gravity, and it will come out to the surface at this point. So it will come to the groundwater level. It cannot go any further, so there is no way it can go any further. So this is a typical situation for rivers. Let's see what can happen when we have a very heavy rainfall, and it will go for several days. In this case, the level in the river will definitely increase, and it can even rise to a very high level here. And you will see that the difference again between the water levels on the right hand side and the water level on the left hand side in the river will increase significantly, which will make the water seep underneath the levee even faster. So this process will intensify, and you can imagine that if this difference keeps increasing, which we're going to call delta H, there will be very high pressure of water at this point. So this very high pressure will decrease the effective stress, and when the effective stress goes to almost zero, we will see natural processes such as liquefaction, quick soil, or we also call it sand boils. So sand boils, it's very dangerous process that may undermine the stability of engineering structures. And now let's see how it actually works in terms of the theory. Let's look at this example where we have water flow in the sandy layer. So this is sandy layer. This sandy layer is a sandwich between the impermeable rock and also clay. In this case, we will assume that clay is impermeable. And we know that there is water flow from point A to point B because if we measure the water flow at point A, if we install piezometer, we will see that the water level at this point, while at point B, when we install piezometer at point B, we will see that the water level is below. So this difference in water levels will cause water to flow from point A to point B. So let's now define the hydraulic gradient, which is the coefficient that shows how fast water can flow from two different points. So what we need to know to define this coefficient is the difference in water levels, delta H, and we also need to know the distance between these 2 points. In this case, we have the distance between point A and point B. Next important parameter that we need to know when we deal with water flow in soil is coefficient of permeability. We're interested in this coefficient in particular because it's a property of soil, and this is what we would like to find out in this course of soil mechanics. This coefficient of permeability is related to the velocity of water flow in soil mass through the hydraulic gradient. As you remember that hydraulic gradient is the difference between delta H and L. You will see that for the hydraulic gradient, there is no any information, anything about soil properties, which means that this hydraulic gradient coefficient doesn't depend on the type of soil at all. So what we also need to remember that for the coefficient of permeability, we use the same units as for velocity, which is meters per second. And this coefficient of permeability varies depending on the type of soil. It will be relatively high for coarse grain material, and it will be relatively low for clay. This table gives you some idea about range of coefficient of permeability for different types of soil. As I already mentioned, that for gravel and sand it will be relatively high compared to the fine grain material like silt and clay. Some clay can be very low to permeate, and it can have very low coefficient of permeability of 10 in the power of -9. Typically it's very plastic clay with lots of clay minerals such as montmorillonite or smectite. In some applications, in some problems that we deal with, we may assume that at some point some clay soils can be impermeable, which means that water cannot penetrate through that soil. Of course, in real life it's not true. Water can still flow through this very impermeable soil, but the rate of flow will be very low. To obtain this coefficient of permeability, we can perform two different tests in the laboratory. So the first one is constant head test. So this is a video where you can see a little bit of theory and the test procedure. So this test we typically perform for gravel and sandy material. The following head test is the test that we would perform for soil with lots of fines, such as silt or clay. Again, here is a link to the video. Please watch it. It gives you test procedure and how to analyze results from such tests. For both tests, we use this concept. In this case, we have velocity. To find velocity, we need to know the amount of water flow. So we just measure it in the test. And we also know the area of the water flow, because the water flows through soil, and we can measure the area of the soil sample. And another thing that we measure is the time. So this is the time necessary to collect a certain amount of water. And once we find the velocity, we can estimate the coefficient of permeability using one of the formulas that I showed in the previous slide.